Hello everyone. Welcome to week 7 class for Saturday session for the course Novel Technologies for Food Processing and Shelf Life Extension. So in this class we will be discussing problems related to week 7 syllabus. And if you guys have any doubts, you can either post it in the in-call messages. If you guys want to discuss any answers also, you can message there, or you can unmute yourself and ask your doubts or answer the question. So we'll start with the first problem. Question 1. Which among the given oil seeds generally does not require pre-pressing step before solvent extraction? A. Sunflower, B. safflower, C. rapeseed, and D. soybean. So if you guys know the answer, you can post it in the in-call messages. Before we answer this question, what is the criteria for not requiring a pre-pressing step? So what kind of oil seeds, what is the quality of the oil seeds that needs to be there that does not require a pre-pressing step before the solvent extraction? So the entire concept of pre-pressing is done when you have too much oil in your seeds. That is, the oil content in your seeds, when they are very high, it generally requires a pre-pressing step before solvent extraction, because the extraction process might not be that efficient to remove all the oil. So you do a previous step before where you press the oil seeds, and that will release all the oils into the from the seeds into the outside environment, which then you can collect by different methods. So when you have seeds with very high oil content, you have to do a pre-pressing step before the solvent extraction. If your oil seeds do not have that high amount of oil content, then you can directly go for a solvent extraction. So among these four options that are given here, the oil seeds differ in their oil content, where soybeans have around 20% by weight of oil, rapeseed have around 40%, safflower has 38%, and sunflower has 42% oil. So as you can see here from all these four options, soybeans are the only kind of oil seeds that have very less oil content. So among these four, it is the soybeans that do not require a pre-pressing step. Whatever oil is present in those seeds can be directly extracted via solvent extraction. Whereas the other seeds, since they have very high oil content, there is a previous step that is required, that is known as pre-pressing, and then we go for solvent extraction. So just to summarize, the higher oil products often require an added step called pre-pressing. The high oil content makes it difficult to adequately flake the oil seeds and cook for solvent extraction without oil coming out of the seed and fouling the equipment. So this is also one of the criteria. So if you the solvent extraction in itself requires some other steps, that such as the flaking, where you kind of flatten the oil seeds, and then you have to cook the oil seeds to increase the plasticity and so. So during these steps, when you have very high oil content, there are chances that these oils will leak out in the previous stage itself. And when you have oil leaking in these equipments, then it kind of fouls the equipment or reduces the efficiency as well. So in order to prevent that, also a pre-pressing step is one of the reasons why we proceed with it. Furthermore, the oil content would require more optimum energy for the removal of solvent from micellar and extraction. That is the same that I was explaining before, that certain amount of oil content is what could be extracted in the solvent extraction, and very high oil content would be difficult to remove only via solvent extraction. Therefore, screw press technology is used before the extraction to prepare high oil seeds for the extraction process. So in a screw press technology that we will discuss later on in these slides, what you'll do is you'll just feed in the oil at one end, and oil seeds in one end, and as the oil seeds passes through this horizontal extruder, which has a screw kind of a screw in the middle of the barrel. So there's a horizontal barrel and there's a screw in the middle of the barrel, and this screw will keep rotating, and because of this rotation there is often friction generated, and whatever oil seeds are passed through it, because of the screw action and the shearing force, oils will leak out and can be collected from a different port. So this is known as a screw press technology. This we'll also discuss in the later slides. So the pre-pressing is done by a screw press technology before proceeding with the solvent extraction in case of high oil seeds. The answer is option D, which has very less oil content. Okay. Moving to question 2. So in case if you guys want me to repeat any question, you can let me know. Which of the following process is responsible for imparting plasticity to oil seeds? A. Decorticating, B. Milling, C. Flaking, and D. Cooking. So what is plasticity in an oil seed? So when you mean oil has a certain plasticity, it is the ability to spread easily or so. So like say butter is more difficult to spread, whereas margarine is more easily to can be easily spread. So the ability to spread and flow is kind of related to the plasticity of oil seeds. So higher the plasticity, more is its ability to be able to spread across a certain surface. So plasticity to oil seeds is imparted so that sticking and everything is prevented while processing the oil, while refining the oil. So among these uh, four processes, which of these impart plasticity to the oil seeds? We'll start one by one to explain what are these four processes. So decorticating or dehulling is the removal of fibrous hull from the seeds. So the seeds that you collect from the sources like say vegetable plants or so will have hulls around the seeds, and first you need to remove this hull and then only process the seeds. So this is done by a process known as decortication or dehulling. And then comes the process of milling. So milling is the grinding of the oil seeds which can be further pressed to extract vegetable oils. Flaking refers to the reduction of oil seeds to a particle size of 0.13 to 0.25 millimeter by rolling. So basically you're kind of trying to flatten it out and form flakes. So the flaking refers to the reduction of the oil seeds by rolling. And the cooking process involves heat treatment where you'll supply certain heat by either steam or so. So the cooking process involves heat treatment which helps in imparting proper plasticity to the seed mass, and it also insolubilizes the phosphatides which are the gums that are present in the oil. So it insolubilizes the phosphatides and related substances to reduce refining losses of oils. So what happens is that your oil has a lot of other constituents such as phosphatides and other substances, coloring agents and so on. And what you require is only the oil, that is the triglycerides that are present in the oil. You do not require all these other products such as these phosphatides and other substances. So while refining the oil, you need to remove these phosphatides at each and every stage. So what cooking does is, in cooking when you increase the temperature by indirect mechanisms like steam or so, when you increase the temperature, this results in the insolubilization or precipitation of these phosphatides and other substances, and then you can remove them in the stage itself. Then you can move on to other refining procedures. So the more earlier you remove the phosphatides, the more better it is, because at each and every stage you will have oil losses also happening along with these other contaminants. You will also have oil losses that are happening at each and every stage. So it is preferably it is more preferred that you insolubilize all these other contaminants as soon as possible and much lesser stages than using for large number of stages and losing oil at each and every stage. So cooking, what happens is, cooking is a pre-step before extraction and refining of the oil. So what it does is, in the cooking process you will heat up the oil, and this will insolubilize all the contaminants and other undesired substances, and this reduces the refining losses of oil. So because of this heating step, the viscosity of the oil also decreases, and this also imparts a proper plasticity to the seed mass. So the answer is option D. Is there any doubt? Okay, moving to question 3. Match the sentences given in the left column with the respective processes in the right column. So A, separation of compounds based on the differences in melting and precipitation points. B. Treatment of oil with caustic soda, and C. Precipitation based on solubility in water. So you have in the second column, you have three processes: degumming, winterization, and neutralization. So these three processes fall under the oil refinery processes, and each of them are involved in removing all those other undesired products that I was discussing in the previous slide. So which one corresponds to what? What is the principle behind each of these? So separation of compounds based on differences in melting and precipitation points. So which does it correspond to? Okay, so we'll discuss each and every process here. So winterization is the process of dissolving the extract in ethanol, then placing the mixture in a freezer to chill. So this cold allows the separation of compounds by differences in their melting and precipitation points. In the cooling processes, the fats and waxes with higher melting points will precipitate out and then can be removed by filtration, centrifugation, decantation, other separation processes. So what happens in winterization? It's very close to crystallization concept only. So where you will dissolve the oil, the extract in a solvent, and then start to freeze it. So because of this freezing process, what will happen is you will first have a crystal nuclei forming, and after the crystal nuclei is formed, you will have the crystal growth as well. And when once the crystal reaches a certain size, we can remove these crystals by different processes as mentioned here. We can either remove by filtration, centrifugation, decantation, and other processes. So in this stage, what is done is based on the differences in melting and precipitation points. So different components in the oil will have different precipitation and melting points. So based on which you can separate them according to your needs. So if fats and waxes have a higher melting point, then those will be able to be separated first easily. Then the other components that have a lower melting point can then be precipitated out. So you'll gradually be decreasing the temperature. So first the fats and waxes which have a higher melting point will precipitate out. Then you can remove those, and then you'll further decrease the temperature to remove any other contaminants possible. So this is the winterization step that corresponds to separation of compounds based on differences in melting and precipitation points. So the second is treatment of oil with caustic soda. So that is done in a process known as neutralization. Sorry. So neutralization or deacidification treats the oil with sodium hydroxide or sodium carbonate to pull out the free fatty acids, the phospholipids, pigments, and waxes. So you will have a slightly acidified oil in the initially fed into the neutralization step, where you will adjust the strength of the caustic soda as per your needs, and based on those strengths you will be able to separate out the free fatty acids, the phospholipids, pigments, and waxes which are not preferred in oil. So oil should have only triglycerides. If it has any free fatty acids, phospholipids, and so on, you need to remove those. So that can be done by the step of neutralization, where you treat the oil with different strengths of caustic soda based on your need. So neutralization corresponds to treatment of oil with caustic soda. And degumming is done by passing hot water through the oil to precipitate out the gums and the proteins that are soluble in water but not in oil, and then discarding the water along with impurities. So what happens is that you will have multiple trays in which, like say in a large column, you'll have multiple trays that contain your oil. And when you pass water through those trays, what will happen is that the uh, gums and proteins that were originally present in the oil will come to the oil water interface. Once it comes to the oil water interface, then you can remove the water, and while the water is being removed, all those other gums and proteins will also be washed away. So now your oil will be free of those gums and proteins, or at least it will get reduced, so that in the next stage you can remove it even further. So degumming is by passing hot water through the oil, where your gums and proteins will come to the surface or the interface of the oil and water, and then you can discard the water along with its impurities. So precipitation based on solubility in water corresponds to degumming process. So A corresponds to 2, B corresponds to 3, and C corresponds to 1. So here this is B, option B corresponds to that. So the answer to this question is option B. Any doubts in these three processes? Basically these three processes, this is the three process and the corresponding principle behind that process that is given in column 1. Okay, question 4. So we have a couple of numericals also in this session. So by combining soybean and sunflower oils, a synergistic oil mixture can be created. If 600 kgs of soybean slurry, which has 20% oil and 80% meal, and sunflower slurry are combined, which has 35% oil and 65% meal, what is the total amount of sunflower slurry that must be blended to get a final slurry combination of 30% oil? So here you can see there are two. In order to visualize this better, I have a diagram. So one of the inlet stream is a soybean slurry, which is around 600 kgs. And here, since we'll be doing an oil balance and a mass balance, I'll be explaining that later. So here it is given that the 20% of the soybean slurry is oil. So let's say that is x1. So x1 is 20% or 0.2. And then you have sunflower slurry also coming in. So let's say that is x kg of sunflower slurry. We don't know the total amount of slurry. That is something that we need to calculate. So x kg of sunflower slurry. Sorry, this is somewhere around 35%. So yeah, sorry. So x2 is the amount of oil present in the sunflower slurry, which is 35%. So x2 is 0.35, and it is already given that only one. It's a combined oil mixture. So you have only one outlet stream coming out. So that also we do not know what is the amount of slurry that is coming out. So let that be y kgs, but we know the amount of oil that is coming out, that is 30%. So x3 is 0.3. So hope this is clear. There are two inlet streams. One is soybean, the other one is sunflower, and there is one outlet stream because both of those oils are blended together. So what we need to do is all these will have simple mass balance equations. So one given here is soybean slurry mass is 600 kgs. X1, that is amount of oil in the soybean slurry mass, is 0.2. X2, which is there in the sunflower slurry, that is oil present in sunflower slurry, is 0.35. Oil present in the outlet stream, is 0.3. So using overall mass balance, so since there is no mass loss or anything of that sort, so there will be an overall mass balance where mass of the soybean slurry plus mass of the sunflower slurry is equal to mass of the blended slurry. That is, input is equal to output. So the two input streams is equal to the output stream. So we already know the mass of the soybean, which is 600. We do not know the mass of the sunflower slurry, which is x, and we do not know the mass of the blended slurry also, so we keep it as y. So is this part clear? We need to find out what is x and what is y, but in the question it is x that is asked. Okay, so we have two equations and two variables and only one equation, so we need to find out another equation. For that we use the oil balance, that is the component balance. So since there is no oil loss or anything mentioned here, so mass of the oil in the soybean slurry plus mass of the oil in the sunflower slurry is equal to mass of the oil in the blended slurry. So mass of oil in the inlet streams is equal to mass of oil in the outlet streams. So in order to calculate what is the mass of the oil in the soybean slurry, it is given that it is 20% oil, which means it is 20% of 600 kgs. That is what we have to calculate. So 600 into x1, which is 20 into 0.2 into 600, plus x, which is the mass of the sunflower slurry, into x2 is equal to y into x3. So 600 into x1 will give you the amount of oil in the soybean. X into X2 will give you the amount of oil in the sunflower slurry, and Y into X3 will give you the amount of oil in the blended slurry. So here we had only percentages. We cannot equate percentage, we need to equate mass, which is why we are multiplying it with the total amount of mass of that stream. When substituting, you get 600 into 0.2 plus X we do not know into 0.35 equal to Y into 0.3. So is this clear as to how we got this component balance? Any doubts, you can ask me to repeat the question. We'll start again as well. Okay, so substituting Y in the equation. So we have now two equations. We have one equation that is coming from the overall mass balance and the other equation that is coming from the component mass balance. Both of them are in terms of X and Y. So you can solve this easily. So we are substituting Y, which is 600 plus X, in this equation. So when you substitute Y here, you have 600 into 0.2 plus X into 0.35 equal to Y, which was 600 plus X, into 0.3. So now you have an equation in terms of X which you can solve for. So X into 0.35 minus 0.3 is equal to 600 into 0.3 minus 0.2. So when you simplify this, you have 0.05 into X is equal to 600 into 0.1. So this is equal to 60, and 60 divided by 0.05 will give you 1200 kgs. So this is the amount of sunflower slurry that you are sending inside the blender, and that is what is asked in the question. So the answer is option C. So any doubts how to solve an extraction process problem? Okay, so we'll be solving more questions like this. So if you guys have any doubts, you can ask. Moving to question 5. Which part of the vacuum bleacher is associated with the shearing action of clay and oil? So A, you have axial blade, B, baffles, C, radial blade, and D, rotating cells. Before we go in, what is the principle behind the bleaching process? So in a bleaching process, you have a process of adsorption where you'll pass in some inert solid or some kind of an adsorbent kind of a material that will absorb all the other undesired components onto your adsorbent. So you'll have an inert solid like say clay in this case that will absorb all the undesired components, and then you can remove these clay and you can regenerate it as well in certain cases. So that is the concept behind using a bleaching process. So there are multiple parts in a vacuum bleacher. So vacuum bleacher will be like a vertical cylindrical structure where you'll have multiple parts. All these correspond to those parts. Axial blade, baffles, and radial blades correspond to those parts. So the vacuum bleach. So to explain it further, the vacuum bleacher is a pressure vessel with 3 to 4 baffles and a top entering agitator. So the baffles are kind of are attached to the walls of the vacuum bleacher inside. So these are attached to the inside of the vacuum bleacher walls, and these baffles are like vertical structures. So if you Google and see, there will be long baffles attached to the walls of the pressure vessel, and because of these baffles, a whirlpool of the oil will be disrupted. So if you keep mixing any liquid continuously in a circular motion, you can often see like a whirlpool like formation that happens. Like even if you do it in a bottle also, you'll be able to see that whirlpool formation when you mix it in a circular manner. So if you have an agitator and you keep mixing it in a circular manner, you'll have a whirlpool formation. So if you have a whirlpool formation, the mixing efficiency, that is the mixing between the oil and the clay, will reduce. And you don't want that. You want your oil to be properly in contact with the clay. So in order to prevent that whirlpool formation and to increase the mixing efficiency, we have baffles in the walls of the bleacher. So this is the role of baffles in a vacuum bleacher. So you have a top entering agitator, which means that you'll have the agitator will be attached to the top of the vessel, And you'll have different kinds of blades to attached to the agitator. You have an axial blade and you have a radial blade. So what the axial blade does is, axial blade will push the oil downwards continuously. So you'll feed the oil seeds and everything at the top of your vacuum bleacher, and it will slowly come down and you can collect the oil at the bottom. So in order to push the oil downwards, you need an axial blade. That is, the movement will be axial or parallel to the agitator shaft. So axial blade will basically push the oil downwards, and the radial blade is what will ensure the mixing process. That is, it is capable of shear action so that the absorbent and the oil are brought to intermittent mixing continuously. So in order for the other components to attach or to absorb onto the clay, you need to make sure that the clay or the adsorbent is in proper contact for as maximum time as possible with the oil, in order to ensure that a proper mixing is necessary. The radial blade uh, helps in this mixing process, and the baffles help in prevention of these whirlpools that are formed during mixing. Whereas the as it is being mixed, it also needs to be pushed down to the bottom of the vacuum bleacher. So to push it down to the bottom of the vacuum bleacher is what you have an axial blade for. And there is no rotating cells in a vacuum bleacher. That is for a different equipment. The answer is option C. Radial blade is the one that causes the shearing action in the mixing of clay and oil. Hope this is clear. Okay, moving to question 6, another numerical problem. 100 kgs of soybeans containing 20% oil are leached with 100 kgs of fresh hexane solvent in a single stage leaching of oil from flaked soybeans using hexane. So you have a leaching process that is happening. You send in 100 kgs of soybeans that contain 20% oil, and you send in 100 kgs of fresh hexane. So your oil will be transferred from soybeans to the hexane solvent. So that is what is happening here. So the slurry underflow N value remains constant at 1.5 kg insoluble solid per kg solution retained. So we need to calculate the overflow and the underflow both in kgs. So before we move forward with the question, we'll just brush up on some basic concepts. So this, let's say this is a representation of an extractor. You have two inlet streams. So one is the soybean slurry, which is 100 kgs, and you know there's 20% oil in it. Let the solute concentration be YA0. And I'll discuss each one of these variables now. But before that, we'll just discuss what are going inside the extractor and what is coming out of the extractor. So you have two streams going in. One is the soybean slurry. The other one is the fresh solvent, which is hexane. And then after the extraction process is complete, you have hexane that has certain amount of oil also coming out. And then you have the rest of the soybean slurry. So this is known as the rest of the soybean slurry after extraction is known as the underflow. And the solvent that now has the oil, majority of the oil, is known as the overflow. So what they are asking is, we need to calculate how much amount of overflow, that is this hexane, and how much amount of underflow, that is this remaining the soybean slurry, is present after the extraction process. So this is what we need to calculate here. So let's consider A as the solute, which is the oil, B as the inert solid. So that will be your meal, or after the whatever is apart from oil will be your inert solid. So that will include often your rest of the meal, your proteins, your water, your carbohydrates, or any other components present apart from oil will be considered as your inert solid. And C will be the solvent, that is the hexane. So let's say A is solute oil, B is inert solids, and C is the solvent. So we'll brush up on certain concepts here. So the basic concept is that the underflow is the stream leaving from the extractor that initially contained the solute, and overflow is the stream leaving the extractor that has the extracted solute. So this is the underflow, this is the overflow. So we'll discuss certain formulas here as well. So here you have in the question something known as N value. So N value is basically the amount of solid divided by the amount of solution. So in any stream, solution is basically the amount of solute plus amount of solvent. So N value is amount of inert solids, that is B, divided by amount of solute plus amount of solvent. Hope this is clear. Hope this is not confusing. If you want me to repeat, I can repeat as well. So N is basically amount of solids divided by amount of solution. So amount of solution, as you can see here, is A plus C. So N is equal to B divided by A plus C. So if you see here, generally in your feed slurry, you do not have any solvent. It is not yet exposed to hexane. So in a feed slurry, your C will always, your majority of the time, C will be 0. So then N will be equal to kg of B divided by kg of A. This is only when your inlet slurry does not have any solvent already present. If it has solvent already present, then this will be the equation. If it does not have any amount of solvent initially, then kg of C goes to 0. So then you have kg by B of kg by A. So this is for the inlet slurry. But if you want to calculate N for the solvent, there is no solid at all in the solvent. It is only fresh hexane coming in. So you have only C here. There is no A, there is no B. So in that case, it is always seen that N is 0. You can't have solids in your solvent, because then everything will settle down. It doesn't make sense. So generally you have fresh solvent or solvent with tiny amount of oil present, but you will definitely not have inert solids in your solvent. So kg of B will always be 0 for your solvent streams. So N is 0 in those cases. So for the solvent stream, N is always equal to 0 as solids are not present. And then and solids are not extracted also. So when you put it inside an extractor, it is only the oil that will be transferred from one stream to another stream. Solids will always remain in the slurry itself. So since solids are never extracted, kg of B will always be equal to 0, and hence N is 0 for the solvent stream. And for the inlet feed slurry, sometimes it does not have the solvent. So then N becomes kg of B by kg of A. Hope this is clear, because with this we will have multiple other problems that are coming in the later slides. So this N is what is given as 1.5 kg of insoluble solid per kg of solution for this stream, that is the underflow. So for this we already know what is N1. Okay, so in our then we will also learn what are the equations for the solute concentration in each of the streams. So for the solute concentration, it is equal to solute divided by solution in any stream, be it the overflow or the underflow. In any stream, it is the amount of solute divided by amount of solution. So in the overflow liquid, we'll call it as XA, and the underflow liquid, we'll just term it as YA. This is just a difference in variable names, but the formula is the same. Kg of A divided by Kg of A plus C for both the streams. So now with the given concepts, we will discuss how to balance the equations. So there are three balances involved. First is the solution balance, that is both A and C should be balanced together. Second is the solute balance, that is only the A component that is balanced. And third is the solid balance, that is the B component that is balanced. So this is again the same picture that is given here in the slide. So here the solution balance, let's say L0 is the solution, that is both A plus C in the inlet stream. L1 is the solution in the underflow, V1 is the solution in the inlet hexane stream, and V2 is the solution in the outlet hexane stream. So L0, L1, V1 and V2 are the solution stream. This solution will have both A component, that is the solute, and C component, that is the solvent. So by doing a mass balance, that is input is equal to output. So in this case, input you have two streams, this one and this one. So solution of this is L0, solution of this is V1. So L0 plus V1, that is total input, is equal to total output. Output is L1 plus V2. So this is the solution balance. L0 plus V1 equal to L1 plus V2. And M is the total amount of mixture solution. So that we will not be discussing now, we will discuss it in the later slide. But this is the solution balance. So second comes the solute balance. So YA0 is the solute concentration in the inlet feed. YA1 is in the underflow solute concentration. xa naught is the solute concentration in the inlet solvent stream, and xa1 is after the extraction whatever is there in the solvent stream. So L naught into Ya1 plus V1 into Xa naught is equal to L1 into Ya1 plus V2 into Xa1. So this will balance all the oils in the four streams. So solute balance is nothing but oil balance. Then you have solid balance. Solid balance is L naught into N naught equal to L1 into N1 equal to M into Nm. So here L naught is this, that is the solution. N naught is amount of solids divided by solution. So L naught into N naught will give you amount of solids alone. So L naught into N naught, and here N is always 0 as I mentioned in the previous slide. In these streams N is always 0, so you need not account for these two streams. So this amount of solids here is equal to amount of solids here. So L naught into N naught is equal to L1 into N1. So hope this is clear. If there is any confusion, you can post it in the discussion forum or mail me as well. We can take this question up again. So M is again the total mass of the solution, and Nm is the total amount of solids in the mixture. So we have Ya naught as 1 because this is the formula for Ya. So kg of A divided by kg of A plus kg of C. Since this stream does not have any C, so this goes to 0. Kg of C goes to 0. So you have kg of A divided by kg of A, hence Ya naught is equal to 1 in the inlet stream, this stream. So Xa naught is 0 because Xa naught is the amount of solute present in the inlet solvent stream. Xa naught is 0 because you do not have any oil coming inside the hexane stream. So Xa naught equal to 0. N1 is already given as 1.5 kg of solid per kg of solution. V1 is given as 100 kg of hexane, and L naught is the amount of solution that is present. So amount of solution is equal to A plus C. Here since you do not have C in this case, it is only equal to A. A is nothing but your solute, which is 20% of oil. So L naught is equal to A plus C. Since C is 0, L naught is equal to A. So A is equal to 20% of oil, which is 20% of 100 kgs. So 100 into 0.2, which is 20 kgs. And then we need to calculate what is the underflow, which is L1, and overflow, which is V2. This is what we need to calculate. So all these are mass balances, which is why it is given in kg units. So hope this is clear. Solution is A plus C. If you do not have C in your stream, then it is only A. Then you have a solute balance, and then you have a solid balance. And generally, since there is no solvent here, Ya is equal to kg of A divided by kg of A, which is equal to 1. And then since majority of the times you do not have any oil in this stream, your Xa naught will always be equal to 0. So we'll start with solution balance. L naught plus V1 is equal to L1 plus V2. So substituting the values here, L naught is 20 kgs as we calculated here, which is 20% oil. V1 is given as 100 kgs. That is equal to L1 plus V2. L1 is this underflow system, V2 is this overflow system. So this is your solution balance. Then we'll go for solid balance. Solid balance is L naught into N naught equal to L1 into N1. So N, as I'm repeating again, N is the kg of solid divided by kg of solution, which is A plus C. So in the inlet stream, per kg of P, you had 20% oil. So the rest is the solid. So 100 into 1 minus 0.2, which is 80% or 80 kg. Sorry. So you have, if 20% is oil, then 80% is the rest of the solid. So 100 into 0.8 will give me 80. And kg of A is 100 into 0.2. And since you do not have any solvent here, it is 0. So you have 80 divided by 20 as your N value, which is equal to 4. 20% is oil, which is kg of A. 80% is solid, which is kg of B. So your N value comes out to 4. Yeah, so now you're substituting N back here. This is nothing but N naught here. So N naught you're substituting back here. You already know what is L naught, which is 20 kgs. You have N naught, which is 4, and N1 is already given in the question into which is 1.5. So from this you can calculate the underflow liquid mass, which is L1, and L1 comes out to be 53.33 kg. So now that you have L1, you can substitute it in the solution balance and then calculate V2. Substituting back in the solution balance, you had 20 plus 100 kgs, which is equal to L1 plus V2. So 120 is equal to 53.33 plus V2, and hence V2 is 66.67 kgs. So this is your overflow. The answer is option B. So these are the formulas that you will be using in a leaching process. So whenever you have three different components that are given, one is the solute, other one is the solid, then the solvent as well. These are the three equations that you will be using to calculate the different solute concentrations, the flow rate, and so on. So we'll have one more question similar to this at the end of the lecture as well. Okay, question 7. Dash type of deodorizer is suitable for emulsifier and interesterified products. So there are different modes of operating a deodorizer where you remove all the odor giving compounds in an oil. So and you'll have multiple other steps also that comes along with the deodorization step. So there are different modes available. One is the batch, one is the continuous, and then the semi-continuous. So among these three, it is the batch deodorizer that is suitable for emulsifier and interesterified products. This is because in a batch deodorizer, you basically have a vessel, a vertical cylinder, and with dish and cone heads. So you'll have stream coming to one end, that is the bottom of the vessel, and this steam is passed through the bleached oil to heat the incoming oil. So you'll have everything will be done in a batch process where you will not be taking out anything. So in a batch process, you will have steam coming in one end, oil coming in the other end, and this will heat up the oil to form the deodorization, to start the deodorization step. So the main advantage of using a deodorization over other types is the flexibility of the incoming oil. So based on the oil quality and all, you can change the process parameters. So and this can majorly be done properly in a batch system. So in a batch system, you will know what kind of oil is coming in, and everything will be done in batches, as the name says. Things will be done in batches instead of continuous supply of oil. You will first supply oil that will be in the vessel for a while, and then you can take out your emulsified or interestified products separately. So based on the incoming oil quality, which you know in a batch process, this can help in changing the process parameters, and hence you can specifically favor emulsified and interesterified products. Whereas in continuous and semi-continuous, where you have continuous supply of oil, the control becomes a little more difficult. So since the control becomes difficult, it is much less favorable for emulsifier and interestified products. So the answer is option C. In a batch, you have better control, so you'll be able to control the production of the separation of emulsified and interesterified products. The answer is option C. So moving to question 8. 1000 kilogram of soybean with an oil content of 18%, 35% protein, 27.1% carbohydrate, 9.4% fiber and ash, and 10.5% moisture are A. So the first process is crushed and pressed, reducing the oil content to 6%. Then extracted with a hexane to get a meal with 0.5% oil. So set up a material balance for the soybean constituents, assuming no loss of the protein or water with the oil. So in both the processes, what is the total loss of oil in kgs? So there are two processes involved here. One is the crushing and pressing, where the oil has reduced from 18% to 6%, and then you have the solvent extraction, where it has further reduced 0.5% in the meal. So now you have to calculate where was the how much oil is being extracted and how much is remaining in the meal. So that can be done by materials balance. And since you have been asked to assume no loss of protein or water in the oil, you can assume that all other constituents apart from oil are constant. So we'll go deeper into the question. So the crushing step has 18% of oil in 1000 kgs of soybean seeds. So the amount of oil in soybean is 18% of 1000 kgs, which is 0.18 into 1000, which is 180 kgs. So the amount of other constituents is 1000 minus 180. So you have either oil and you have other than oil constituents. So if oil is 180 kgs, then the other constituents are 1000 kgs minus 180 kgs, which is 820 kgs. And since it has been asked that you are assuming no loss of protein or water with the oil, you can assume that this 820 kgs is constant in all the processes. Then you can do a solid balance, and from there you can calculate the oil balance as well. So it is given here that your crushed and pressed, after it is crushed and pressed, your oil content is reduced to 6%, which means after crushing and pressing, you have 6 parts of oil and then 94 parts of other components. So since the other constituents are constant, it will always be equal to 820 kgs. And since you have 94 parts of the other constituents, so 0.94 into some m, which we do not know what it is, will always be equal to 820 kgs, because your other constituents are kept constant. So this is the balance for other solids. So 0.94 into m is equal to 820 kgs, where m is the total amount of crushed feed. So from there you can calculate m as 820 by 0.94 kgs. So this is the total amount of m, and in this m, 94% is the solid, 6% is oil, as mentioned before. So the amount of oil crushed and obtained is 0.06 of m, which is amount of oil is 0.06 into 820 divided by 0.94. So you have amount of oil, which is 6% of your total mass, that is given as 0.06 into 820 divided by 0.94. So this is equal to 52.34 kgs. Sorry. So if this is the amount of oil that is obtained after crushing, then what is lost is your initial oil minus whatever amount that is remaining. So initially you had 180 kgs, and after crushing this is what you have, 52.34 kgs in the meal. So 180 kgs minus 52.34 will be the amount of oil that is lost in the process. So that is equal to 127.66 kgs. 180 minus 52.34, that will give you 127.66 kgs. So this is the amount of oil lost in the crushing step. So after the crushing step, you are again subjecting it to a solvent extraction process. So in a solvent extraction process, it is already given in the question that you have 0.5 parts oil and 99.5 parts of other constituents. So again, since the other constituents are constant are assumed to be constant, 0.995 into some other m. This m is not the same as m. So let's say this is m1, this is m2. So 0.995 into m2 will be equal to 820 kgs. Since the amount of solids is always constant, so this will remain the same. So 0.995 into m2 is equal to 820 kgs. So m2 will now be 820 divided by 0.995 kgs. So this is the total amount of mass after the solvent extraction process. In a similar way, how you calculated the amount of oil from the total mass, we can again calculate the amount of oil extracted from this. So the amount of oil extracted is 0.5 parts, which is 0.005 into m. That comes out to be 4.12 kgs. So what you have is 4.12 kgs, and hence the amount of oil lost in the extraction. So you had already lost a lot, and you had only 52.34 left. So from that 52.34, you again have only 4.1 kgs, and the rest is lost. So 52.34 minus 4.1 kgs, which is equal to 48.24 kgs. So to summarize, the amount of oil lost in the crushing stage is 127.66 kgs and the amount of oil lost in the extraction stage is 48.24 kgs. The answer is option A. So just to give a recap, since the amount of solids is constant, you do a mass balance for the solids. From there, you will get a total mass of the stream. From the total mass of the stream, you already know how much percentage is oil. In case of the crushing step, there was 6% of oil. In case of the extraction step, there was 0.05% of oil. So you know what is the oil that is remaining. So from there, you can calculate how much of the oil was lost. The answer is option A. Moving to question 9. In a single stage batch extractor, 1000 kgs of crushed oil seed, which is 19.5% oil and 80.5% meal, is extracted with 1500 kgs of pure hexane. The solid feed and the solvent are charged in the extractor and kept in intimate contact. The mixture is then allowed to settle for oil diffusion. After a certain time, the solute concentration in the underflow and the overflow system was found to be 0.04 and 0.114 respectively. So calculate the total percentage of oil extracted in the overflow stream. So to give a pictorial representation here, you have again four streams in the extraction process. One is the inlet feed stream that is 1000 kgs that has 19.5% oil, and then you have an inlet solvent stream which is 1500 kgs of 1500 kgs of the solvent. So you have 1500 kgs of hexane coming in. Then after the extraction process, you have an underflow and you have an overflow. Using the total mass balance, let's say F0 is the total mass of the inlet feed, F1 is the total mass of the underflow, S0 is the total mass of the solvent flow, and S1 is the total mass of the overflow. So inlet is equal to outlet, that is F0 plus S0 is equal to F1 plus S1. And the oil balance is F0 into XF0, which is the amount of XF0, let that be the solute concentration in the feed stream. Then you have S0 into XS0, which is equal to F1 into XF1 plus S1 into XS1. So here X stands for the concentration of the solute, that is the oil, in each and every stream. So here we already know what is F0, which is 1000 kgs. We know XF0, which is 0.195. Since it is a pure hexane given, it does not have any oil. So XS0 is 0. So before that, let's just do the total mass balance. So total mass balance is equal to 1000 kgs plus 1500 kgs is equal to F1 plus S1. We still do not know what is F1 plus S1. We will calculate that in the later steps. So F1 plus S1 is equal to total of 2500 kgs. So moving on to oil balance. Oil balance 1000 kgs is F0, 19.5%, that is 0.195 is the amount of solute in the inlet stream. The hexane is pure, so S0 is 0. Then the solute concentration of the underflow and the overflow are already given in the question. That is 0.04 in the underflow and 0.114 in the overflow. So now you have two equations and two unknowns. So this, when you simplify, you have 0.04 of F1 plus 0.114 of S1 is equal to 195. So you have two equations. You can solve the two equations. That is, I'm substituting the substituting for F1 from the previous equation, that is your total mass balance, into this equation. So then you get, by solving this equation, you get S1 is equal to 1283.78 kgs and F1 is equal to 1216.22 kgs. So in any of these extraction processes or leaching processes, if you do a mass balance itself, you will get all the answers. So the amount of oil in the overflow is equal to 0.114 into 1283.78. 0.114 was the solute concentration in terms of fraction. So 0.114 into 1283.78 will give you in terms of kgs, which is equal to 146.35 kgs in the overflow. So S was your overflow, F was your underflow. And since that had 11.114 amount of solute, so 0.114 into S1, that is your 1283.78, will give me the total amount of oil in the overflow, which is 146.35. So this is the oil that was extracted from the feed to the into the hexane. So we need to calculate the percentage of oil extracted. So the percentage of oil extracted is the oil in the overflow that is extracted divided by the initial amount of oil that was present in the feed into 100. So the percentage of oil extracted is 146.35, and the initial amount of oil in the feed is 19.5% of 1000 kgs. So this is your 19.5% was your oil content, and 1000 kgs was your total amount of feed. So 0.195 into 1000 will give you the total amount of oil in the feeds. That is equal to 195 into 100, which is 75.05. So this is the percentage of oil extracted. So the answer is option A. So question 10. In which of the following step of the edible oil refining process, the citric acid is added towards the end of the process? So you have 4 processes. The principle behind these 4 processes are already discussed in the previous slide. So the citric acid is added to the deodorized oil at the cooling stage of the deodorization process, which acts as a chelating agent to complex with trace metals. So often your oil will have trace metals such as magnesium, calcium and so on, sodium. So calcium, magnesium, sodium will all be present in your oil, and to remove those trace metals, citric acid is added towards the end of the deodorization process at the cooling stage. So in the deodorization process, you will actually heat up the oil and then you will bring it back to a cooling stage as well. So during that cooling stage, you will add citric acid. So in a deodorization process, you will heat the oil and then you will cool it back as well. And during the cooling process, you will add citric acid. So citric acid will act as a chelating agent to complex with all the trace metals, and then you can remove this along to remove all the trace metals as well. So the required conditions for the citric acid is a dosage of 50 parts per million and a temperature of 143 degrees Celsius under normal vacuum with the stripping stream. So this is the citric acid dosage that is added, and this will help to bind to the trace metals and decompose the residual soaps that are present in the oil. So this citric acid is added in the process of deodorization. So answer is option A. Moving to question 11. Which of the following is not the characteristic feature of an enzymatic interesterification? Any clue? So you have A, low temperature, B, catalyst specificity, C, low byproducts, and D, dark color of oil. Okay, so in an interesterification process, what happens is that you have the glycerol bone of the triglycerides intact, but then the functional groups will keep swapping. So from R1 you can change it to R2, from R2 you can change it to R3. So the relative position of the functional groups, the side chain functional groups, will be swapped or will be changed. So that is what happens in an interesterification process. So there are two kinds of interesterification process. One is the chemical, second is the enzymatic. So in a chemical process, it often happens at a very high temperature. So because you ensure that that process happens in a very high temperature, what happens is that the oil color will start changing into a dark oil. So even if you cook in oil, you can see that before cooking your oil will be in a different color, and after cooking your oil will be in a different color. So heat kind of induces this dark color in oil. So chemical interesterification, since they are done at high temperatures, that imparts a dark color of the oil. Whereas in case of an enzymatic interesterification, since you are dealing with enzymes here, Enzymes require an optimal temperature and optimal pH for it to function. And this temperature is actually lower when compared to that of a chemical method. So enzymatic interesterification happens at a lower temperature, and since we are dealing with enzymes, enzymes are very very specific to their substrate, and hence the products are also very specific. So you do not get any much byproducts as well. So it's a very very specific process, and you can get the desired uh, interesterified product that you want if you add enzymes instead of chemical processes. So in a chemical interesterification process, you use variety of chemicals and a high temperature and pressure that produces the dark color of the oil and more byproducts. Whereas in case of an enzymatic interesterification, since it's a biologically derived enzyme, it has a lot of stereospecificity and selectivity. So it can specifically change only what you want. It will produce lesser byproducts. It will have higher specificity. And since we are dealing with enzymes or proteins, these require a much lower temperature than that of a chemical process. And because we use a lower temperature, this does not result in the dark color of the oil. So amongst these four, dark color of the oil is not the characteristic feature of the enzymatic interesterification process. So the answer is option D. Hope this is clear. Moving to question 12. Identify the zones of the material flow in below given schematic of the screw press expeller. So this is very similar to the extrusion process that we discussed in 2 weeks back. So here you will have oil seeds passing through one end, and that passing in the hopper, and that will gradually be moved from one direction to another direction. And as it is being moved, your pressure will slowly increase, your temperature will also increase, and because of this increase in temperature and pressure, your oil will leak out of the seeds, and then you can collect these oils at one of the outlet regions, and whatever is there, the remaining part will be expand because of very very high pressure. Once it reaches the pressure, once the pressure is released here at this stage, whatever was being passed, that is the cake or the meal that was being passed, will now expand. So not explain better, in the feeding zone, that is the first part, is where your oil seeds are fed into the expeller from the hopper. So this is the hopper. So oil seeds are fed into the feeding zone. Then you have a transportation zone, that is from the feeding zone it will be transported to a high compression zone. So second comes the transporter zone, so that will be transporting the seeds from one zone to another zone. So then you have the compression zone. In compression zones, because of the rotatory motion of this screw, this is actually a screw or a helical screw. So because of this rotating motion of the helical screw, and plus because of high pressure maintained inside the barrel, you will have a compression zone, that is compression zone, that will compress all the oil seeds that you are passing through. So third comes the compression zone, and at this stage, by the end of the expeller, the pressure will be so high that this is where the extrusion, majority of the extrusion will take place. So this is known as the extrusion zone. So after this extrusion zone, suddenly this area will have very high pressure. This will not have any much pressure at all. So because of the sudden release of pressure, this will cause an expansion of the meal. So this is where your meal expansion will happen. So first is your feeding zone, second is the transportation zone, third is the compression zone where your pressure will gradually increase, and fourth is where you will have the extrusion zone that is happening, where you will have your pressing of the oil from the oil seeds. So answer is option C. Okay. If there's any doubt, you can post it in the in-call messages or unmute yourself and ask. So moving to question 13. For an enzymatic interesterification, a spherical reactor of 2 meter height is filled with peanut oil. Sorry. so for an enzymatic interesterification process, a spherical reactor of 2 meter height is filled with peanut oil of specific gravity 0.92. If the pressure measured at the highest point of the reactor, that is the top of the reactor, is 70 kilopascals, calculate the greatest pressure in the reactor. So, in any reactor or in any column kind of a vessel, where is the maximum pressure that you can obtain? So you have, let's say you have a cylindrical reactor and you have a certain height of liquid also present inside the reactor. So the greatest pressure will be obtained at the bottommost point of the reactor. So highest pressure is experienced at the bottom of the reactor, where you have pressure due to the topmost point also, plus the pressure due to the liquid. So you have a long height of the liquid also. So that liquid will impart pressure at the bottom, and apart from that pressure, you will also have pressure at the top of the reactor. So both these pressures will be acting at the bottommost point, and hence that bottommost point will be the point having the highest pressure. So we need to calculate the basically the pressure at the bottommost point of the reactor. So given here is a specific gravity of 0.92. The height of the liquid is given as 2 meters, and pressure at the highest point is already given as 70 kilopascals. So how do you go about with this question? How do you calculate the pressure at any point due to a liquid? Okay, so before we go that, how do you for the calculation of pressure, we need the density of the fluid. So the density of the fluid can be calculated from the specific gravity. So as we all know, specific gravity is equal to density of the material divided by density of water. So specific gravity is given here. Density of water is 1000 kg per meter cube. So from there we can calculate the density of the oil. So density of oil is equal to 0.92 into 1000 kg per meter cube, which is 920 kg per meter cube. So now we have the density of the oil. With the density of the oil, we can calculate what is the pressure due to the liquid. So the pressure due to a height of a fluid can be given as rho into g into h, where rho is the density, g is the acceleration due to gravity, and h is the height of the liquid. So you have rho now, which is 920 kg per meter cube, g is 9.81, and height of the liquid is given as 2 meters. So from this, you can calculate what is the pressure exerted by the liquid. So if you substitute the values, you get 920 into 9.81 into 2, which is 18.05 kilopascals. So in the question, you already have the pressure due to the topmost part of the reactor. Then now you have calculated the pressure due to the liquid as well. So when you sum both, that will be the maximum pressure that is experienced at the bottom of the tank. So maximum pressure is equal to pressure due to the liquid or the oil plus pressure at the top. So this is equal to 18.05 kilopascals plus 70 kilopascals, which is equal to 88.05 kilopascals. So the answer is option B. Any doubts in this concept? So if you guys have any doubts, you can ask in the in-call messages, or you can ask me to repeat the question. We can take that question again. Okay, so question 14. So 14 to 18 will be based on the same question, but will be asked different questions from the same passage. So a continuous countercurrent multi-stage system is to be used to leach oil from a meal by benzene solvent. The process is to treat 1000 kg per hour of inert solid meal B containing 500 kg oil A and also 50 kg benzene C. The inlet flow per hour of the fresh solvent mixture contains 1000 kg of benzene and 20 kg of oil. The leached solids are to contain 120 kg oil. The settling experiments, similar to those in the actual extractor, show that The solution retained depends upon the concentration of the oil in the solution. So the last line is not important. What we need is the rest of the parameters. So calculate the amount of inlet solution with untreated solids. So in a leaching process, what streams constitute the solution? So you have four streams here. So one stream is the inlet stream that contains the meal and the oil along with some benzene. That is your feed inlet. Then you have a feed outlet. That is your second stream. Third stream is the solvent inlet. Fourth stream is the solvent outlet. So you have four streams coming into this system. So calculate the amount of inlet solution with the untreated solids, that is the inlet stream. When you mean untreated solids, it is the inlet stream that is being asked here. The inlet solution, what two streams constitute the inlet solution? Okay, so when you mean solution, it is always equal to the total amount of solute that is given as A here and the total amount of solvent that is given as C here. Sorry, this is C, not B. So the total amount of solution in any stream is equal to total amount of solute plus total amount of solvent. So here it is asked what is the inlet solution. So in the inlet stream, what is the total amount of solution that you can get here? So in the inlet stream, your amount of oil in the inlet feed is 500 kg per hour. You're having a basis of 1 hour as the basis. So the total amount of oil or the solute is 500 kg per hour. And total amount of solvent or the benzene here is 50 kg per hour. So the total amount of solution is 500 plus 50, which is equal to 550 kg per hour. So this is how you calculate the solution in any stream. That is A plus C will be equal to your solution. A being the solute, C being the solvent, B being the inert solids. So the answer is option C. Hope this is clear. So question 15, the same question but same passage but a different question. So what will be the concentration of the solute in the feed? So in a leaching process, how do you find the concentration of a solute? So in any feed, any stream, the concentration of a solute in a stream can be given as kg of A divided by kg of A plus C. That is the amount of solute divided by total amount of solution. A plus C is your solution, A is your solute. So in any stream, be it feed or be it an extract solvent stream or anything, the amount of solute in a stream can be calculated as kg of A divided by kg of A plus C. So we need to calculate what is the concentration of the solute in the inlet stream, in the inlet feed stream. So we already know in the inlet feed stream 500 kg is the amount of oil and then 50 kg is the amount of benzene, that is your C. So 500 divided by 500 plus 50 will give me the amount of solute in the inlet feed stream, which is 0.91. The answer is option A. Hope this is clear. Question 16. So determine the inlet leaching solution in kg per hour. So it's the same formula as we used in question 14. So here in this case, instead of finding it in the feed inlet, we need to find it in the solvent inlet, the fresh solvent inlet. So what is the solution, amount of solution in the fresh solvent inlet? Solution is always equal to A plus C. So what is the value here? So this corresponds to your fresh solvent inlet. So you have 1000 kg of benzene, which is C, and 20 kg of oil, which is A. The total amount of solution in stream is equal to amount of solute plus amount of solvent. So in a leaching stream, the amount of leaching solution is equal to amount of oil or solute plus amount of solvent or benzene. So oil is 20 kgs, benzene is 1000 kgs. So the total amount of leaching solution is 1020 kg per hour. Answer is option C. Any doubts? Anything that needs to be repeated? Okay. Question 17. The same question, same passage. Calculate the solute concentration in the solvent. So the inlet solvent, we need to calculate the total amount of solute concentration in the inlet solvent. So how much is it coming out? How do you calculate that? The same as question 15 here. Amount of solute in a stream is equal to A divided by A plus C. That is solute divided by solution. So in the solvent stream, you have 20 kgs of oil, and your C is 1000 kgs. So 20 divided by 20 plus 1000, that comes out to be 0.0196. That is your solute concentration. Answer is C. The last question in this passage, what will be the total mixture flow rate and its concentration? So what do you mean by total mixture flow rate? So let's say this is the diagram of the extractor. You have two feeds coming in. One is the feed inlet, one is the benzene inlet. Then you have the underflow slurry that has minimal amount of oil left, and then you have the overflow benzene that has maximum amount of the oil that was extracted. So you have 4 streams. So how do you calculate the total mixture flow rate? So the amount of mixture, the total mixture flow rate can be given as, let's say, M and Xm. So the total amount of mixture flow rate is either the total solution in the inlet streams or the total solution in the outlet streams. Both are the same. The sum of either all the inlet or the outlet solution stream is equal to the total mixture flow rate. So let's say L0 is the solution stream in the feed inlet, L1 is the solution in the feed outlet, V1 is in the solvent inlet, and V2 is in the solvent outlet. So the total amount of solution stream either in the inlet or the outlet is equal to your M, that is your total mixture. So L0 plus V1 will be your total inlet streams, L1 and V2 will be your outlet streams. So this is the solution stream, not the entire stream that you need to take care. So L0 plus V1 is equal to M. So we do not know L1 and V2, that is not given in the question. So we'll ignore this, we'll calculate M from the inlet stream itself. So L0 we calculated in the question 14, that is your A plus C. A is 500, C is 50, so 550 is your L0, that is the solution in the inlet stream. Similarly, in case of the solvent stream, A plus C, that is 1000 kgs plus 20 kgs, which is 1020. So M is 1570 kg per hour. Is this clear? Total amount of solution in the inlet, that includes both the streams, that will be equal to your M. So we already know what is M, which is 1570 here. We need to calculate what is the concentration in the mixture. So in order to calculate the concentration, this was an overall balance. We need to in order to calculate the concentration, we need to do a component balance. So that component will be oil. So the total amount of oil in the inlet feed plus total amount of oil in the inlet solvent is equal to total amount of oil in the outlet feed and amount of oil in the outlet exit. So oil in the inlet is equal to oil in the outlet. That is what it basically means. So this corresponds to the inlet feed, this corresponds to inlet hexane, this corresponds to your outlet slurry, this corresponds to your outlet hexane. So inlet is equal to outlet. So that is equal to again m into xam, where m is the total amount of mixture flow rate and xam is the solute concentration in the mixture. So we know what is L naught, we know what is V1. So we'll calculate from the inlet streams itself. And y A naught we calculated from the previous questions. A divided by A plus C, that was your y A naught. So that was 550 into 0.91 plus 1020 into 0.0196. This was again A divided by A plus C in the hexane stream. So we are basically using the solutions from the previous question to solve this question. Any doubts in this? How 0.91 and 0.0196 came? If anything needs to be repeated, kindly let me know. So solution is calculated by A plus C. Solute concentration is calculated by A divided by A plus C. That is how these values came from the previous questions. So from this, you can calculate XAM, which is 0.33. So this is your solute concentration in the mixture. The answer is option B. In case any question needs to be repeated, kindly let me know. So question 19. Which of the following is not utilized as a catalyst in chemical interesterification process? So again, as I mentioned, interesterification is the process in which you will keep the glycerol backbone the same in the triglycerides, but you will swap or change the functional groups, the R groups that are present in this present as your side chain. So there are two methods, chemical and enzymatic, that we discussed before. So in chemical interesterification, you need a chemical compound as a catalyst. So among these four, which of those are not utilized as a catalyst? So the answer is the acetate of zinc and tin are high temperature catalysts. That is, you need to raise the temperature of the oil for these catalysts to work. So this is a high temperature catalyst, whereas sodium ethylate is a low temperature catalyst. So these three are used in the chemical interesterification process at different temperatures. However, the aluminum acetate is not a catalyst used in any of these processes. It is in fact used to treat, it is used as an antiseptic agent to treat inflammation, itching of infected skin, and promotes healing. So aluminum acetate is not a catalyst, the rest three are. The answer is option D. Any doubts so far? Okay, moving to question 20. Dash is provided to permit the drainage of oil in a screw press oil extractor. So screw press oil extractor will press all the oil seeds to leak out all the oil that is present. So it will not be a 100% efficient process, but in case of high oil containing seeds like sunflower seeds or so, a pre-pressing is done to press out all the oils in the screw press oil extractor, and after this you can go for a solvent extraction process, the same thing that we discussed in question 1. So in a screw press oil extractor, as the pressure is increased, all the oil present in your seeds will start coming out. So you need to drain this oil to release this pressure. So this drainage of oil is done by one of these four parts. So which one of these is used to permit the drainage of oil? So this is the diagram of a screw press oil. You have a feed hopper here where you'll send in the seeds that contain the oil, and here you can see a a helical screw like structure, and this screw like extruder will continuously rotate, and because of this rotation process you will have friction, and on top of that you will increase the pressure inside the barrel also. So because of this you will maintain a very high pressure inside, and there will be a rotating force in the screw also. Because of this, there will be a friction generated, and because of this friction, your oil seeds will press and oil will leak out. So this oil is leaked out or drained using something known as a spacer. So here in this figure it is not mentioned, but you will have spacers here in this region that will remove off all the oil, that will permit the drainage of the oil as the pressure of the feed material is increased. So rings, there'll be rings present here. These rings are used to increase the pressure buildup in the material. So only if you increase the pressure, you will be able to squeeze out all the oil. So rings or pressure rings are used to increase the pressure buildup in the material. And in the discharge end, you see something known as a choke. So this choke can be controlled to to either increase or decrease the pressure that is present inside the barrel. So if you increase the annular space, that is, there's a lot of space in the barrel, then your pressure will decrease. But if you are trying to squeeze something through a very small hole, that is, if you decrease the annular space, then the pressure buildup will also increase. So you can adjust the choke to adjust this annular space, and accordingly the pressure inside the system will also change. So if you are trying to squeeze something through a small hole, pressure will be high. If you are trying to squeeze something through a large hole, you do not require that much amount of pressure. So the choke can be used to alter this annular space, and because of this pressing, you will get something known as a cake. And while the oil is drained out, whatever is left out will be this cake. The answer is option B. Spacer is what is used to drain all the oil as the pressure is increased. Any doubt in this so far? Or any other question that needs to be repeated? Okay, if not, then we end today's session. If you guys have any doubts, you can post it right now, or you can post it in the discussion forum, or you can mail me through this as well, through the mail ID given here. These slides and the recording session will be made available to you very soon.